Hydrofluoric acid is a solution of hydrogen fluoride in water. It is a precursor to almost all fluorine compounds, including pharmaceuticals such as fluoxetine, diverse materials such as PTFE, and elemental fluorine itself. It is a colourless solution that is highly corrosive, capable of dissolving many materials, especially oxides. Its ability to dissolve glass has been known since the 17th century, even before Carl Wilhelm Scheele prepared it in large quantities in 1771. Because of its high reactivity toward glass and moderate reactivity toward many metals, hydrofluoric acid is usually stored in plastic containers. Hydrogen fluoride gas is an acute poison that may immediately and permanently damage lungs and the corneas of the eyes. Aqueous hydrofluoric acid is a contact poison with the potential for deep, initially painless burns and ensuing tissue death. By interfering with body calcium metabolism, the concentrated acid may also cause systemic toxicity and eventual cardiac arrest and fatality, after contact with as little as 160 cm2 of skin. Acidity. Hydrofluoric acid is classified as a weak acid because of its lower dissociation constant compared to the strong acids. It ionizes in aqueous solution in a similar fashion to other common acids, HF plus H2OH3O plus Fa. It is the only hydrohalic acid that is not considered a strong acid, that is, it does not fully ionize in dilute aqueous solutions. When the concentration of HF approaches 100%, the acidity increases dramatically because of homosociation, 3HFH2F++ FHFA. The bifluoride anion is stabilized by the very strong hydrogen-to-urofluorine hydrogen bond. Production. Hydrofluoric acid is produced by treatment of the mineral fluorite with concentrated sulfuric acid. When combined at 265 degrees Celsius, these two substances react to produce hydrogen fluoride and calcium sulfate according to the following chemical equation: KF2 plus H2SO4 2HF plus CaSO4. Although bulk fluorite is a suitable precursor and a major source of world HF production, HF is also produced as a byproduct of the production of phosphoric acid, which is derived from the mineral apatite. Apatite sources typically contain a few percent of fluoroapatite, acid digestion of which releases gaseous stream consisting of sulfur dioxide, water, and HF, as well as particulates. After separation from the solids, the gases are treated with sulfuric acid and oleum to afford anhydrous HF. Owing to the corrosive nature of HF, its production is accompanied by the dissolution of silicate minerals, and, in this way, significant amounts of fluorosilicic acid is generated. Uses: oil refining. In a standard oil refinery process known as alkylation, isobutane is alkylated with low molecular weight alkanes in the presence of the strong acid catalyst derived from hydrofluoric acid. The catalyst protonates the alkanes to produce reactive carbocations, which alkylate isobutane. The reaction is carried out at mild temperatures in a two-phase reaction. Production of organofluorine compounds. The principal use of hydrofluoric acid is in organofluorine chemistry. Many organofluorine compounds are prepared using HF as the fluorine source, including Teflon, fluoropolymers, fluorocarbons, and refrigerants such as Freon. Production of fluorides. Most high-volume inorganic fluoride compounds are prepared from hydrofluoric acid. Foremost are Al3-Alf6, cryolite, and Alf3, aluminium trifluoride. A molten mixture of these solids serves as a high-temperature solvent for the production of metallic aluminium. Given concerns about fluorides in the environment, alternative technologies are being sought. Other inorganic fluorides prepared from hydrofluoric acid include sodium fluoride and uranium hexafluoride. A chant and cleaning agent. In metalworking, hydrofluoric acid is used as a pickling agent to remove oxides and other impurities from stainless and carbon steels because of its limited ability to dissolve steel. It is used in the semiconductor industry as a major component of right etch and buffered oxide etch, which are used to clean silicon wafers. In a similar manner it is also used to etch glass by reacting with silicon dioxide to form gaseous or water-soluble silicon fluorides. CO2 plus 4HF or CF4, G, plus 2 hours 2O, CO2 plus 6HFAH2CF6 plus 2 hours 20, a 5% to 9% hydrofluoric acid gel is also commonly used to etch all ceramic dental restorations to improve bonding. For similar reasons, dilute hydrofluoric acid is a component of household rust stain remover and in car washes and wheel cleaner compounds. Because of its ability to dissolve iron oxides as well as silica-based contaminants, hydrofluoric acid is used in pre-commissioning boilers that produce high-pressure steam. Niche applications. Because of its ability to dissolve oxides and silicates, hydrofluoric acid is useful for dissolving rock samples prior to analysis. In similar manner, this acid is used in acid macerations to extract organic fossils from silicate rocks. Fossiliferous rock may be immersed directly into the acid, or a cellulose nitrate film may be applied, which adheres to the organic component and allows the rock to be dissolved around it. Diluted hydrofluoric acid is used in the petroleum industry in a mixture with other acids in order to stimulate the production of water, oil, and gas wells specifically where sandstone is involved. Hydrofluoric acid is also used by some collectors of antique glass bottles to remove so-called sickness from the glass, caused by acids attacking the soda content of the glass. Health and safety. In addition to being a highly corrosive liquid, hydrofluoric acid is also a contact poison. It should therefore be handled with extreme care, using protective equipment and safety precautions beyond those used with other mineral acids. Owing to its low acid dissociation constant, HF as a neutral lipid-soluble molecule penetrates tissue more rapidly than typical mineral acids. Because of the ability of hydrofluoric acid to penetrate tissue, poisoning can occur readily through exposure of skin or eyes, or when inhaled or swallowed. Symptoms of exposure to hydrofluoric acid may not be immediately evident, and this can provide false reassurance to victims, causing them to delay medical treatment. HF interferes with nerve function, meaning that burns may not initially be painful. Accidental exposures can go unnoticed, delaying treatment and increasing the extent and seriousness of the injury. Once absorbed into blood through the skin, it reacts with blood calcium and may cause cardiac arrest. Burns with areas larger than 160 cm2 have the potential to cause serious systemic toxicity from interference with blood and tissue calcium levels. In the body, hydrofluoric acid reacts with the ubiquitous biologically important ions Ca2+ and Mg2+. Formation of insoluble calcium fluoride is proposed as the etiology for both precipitous fall in serum calcium and the severe pain associated with tissue toxicity. In some cases, exposures can lead to hypocalcemia. Thus, hydrofluoric acid exposure is often treated with calcium gluconate, a source of Ca2+ that sequesters the fluoride ions. HF chemical burns can be treated with a water wash and 2.5% calcium gluconate gel or special rinsing solutions. However, because it is absorbed, medical treatment is necessary. Rinsing off is not enough. Intra-arterial infusions of calcium chloride have also shown great effectiveness in treating burns. Hydrogen fluoride is generated upon combustion of many fluorine-containing compounds such as products containing boron and polytetrafluoroethylene parts. Hydrofluorocarbons in automatic fire suppression systems can release hydrogen fluoride at high temperatures, and this has led to deaths from acute respiratory failure in military personnel when a rocket-propelled grenade hit the fire suppression system in their vehicle. See also, vapor phase decomposition, references. External links, International Chemical Safety Card 0283, NIOSH Pocket Guide to Chemical Hazards, CID 14917 from PubChem, CID 144681 from PubChem, CID 141165 from PubChem, CID 144682 from PubChem, Hydrofluoric acid burn. The New England Journal of Medicine Acid Burn Case Study.